In the last video, we talked about DNA gel electrophoresis, and we started talking about how this thing is going to look when we start analyzing a DNA sample. So we said there were going to be a couple of wells up here, and each well will hold a DNA sample. It might be yours, it might be someone else's, it might be your mother's, it might be your father's, it might be your sister's. It could be a suspect, it could be a murderer for all we know. But any type of DNA sample will be held up here in the well. In the first one, though, we said that we normally hold a ladder. And the purpose of the ladder is to make bands. We know those bands are there, and we know how many should actually show up. So I want to talk a little bit more about this ladder. That way you're becoming more familiar with it, and we know exactly what to do with this ladder if we have to do anything kind of scientific other than just looking at the banding patterns. And by the way, we are really kind of talking about genomics right now. I mean, that's kind of this whole field, not entirely, but it's part of it. How does DNA cleave and fragment up and break up into the pieces? And let's look at number of base pairs and everything else. So just in case you're wondering, we're kind of venturing off into the biotechnology side of the house a little bit versus more of the chemistry side of the house. So this ladder will typically come with an insert, and an insert is just basically a piece of paper, of course, when you order the ladder. And this insert will basically describe the base pairs that should appear in the well. So they're going to give me a picture that looks very similar to this, and they're going to say, listen, when you perform this electrophoresis and you put the ladder in one of the wells and you develop it, these are the number of bands that you should see. And they're going to give you a picture of what they're supposed to look like, how close they are and everything. And then in addition to that picture, they're going to list the number of base pairs as far as fragments go for each band. So, for example, they might say that this one is 4,000. They might say that this one is 3,500. They might say that this one represents 2,000. This one's going to be 1,600. And maybe this is going to be 900. Who knows? But they're going to give me some information about it, because I'm going to have to use this sooner or later in order to do more scientific work on the electrophoresis gel. All right, so that is the purpose of the ladder. It will come with a sheet of paper, or someone will have to tell me what the bands are supposed to represent. I should see that number of bands if I've developed my electrophoresis the proper way. If I do not see that number of bands, then that means I did not develop it properly. My agarose gel is made wrong. My buffer is made wrong. Maybe I should have let it run a little bit longer, but I should see the number that they give me in the insert. And each band represents a number of base pairs. So then I'm going to run a sample. And the sample, we said, might not actually perfectly match the ladder, which is okay. That's not what we want. That's not what we're after. We know it's not going to. But we can at least use the ladder initially to estimate the base pairs that I have with this extra DNA sample that I've ran. If I take a look at this first one, let me change the color on you a little bit. If I take a look at this first fragment, and I kind of come over, and I compare that to the ladder, I'm going to see that we're a little bit below 4,000. So estimation-wise, I'm going to say that this could be 3,900, 3,800, somewhere in there. We just don't know, but we can estimate it. I can do the same thing for the next one, right? I can look at this band, I can come over to the DNA ladder, and I can estimate that base pair size. So that particular fragment is going to be more than 2,000, I know. So I can say 2,200, 2,400, maybe somewhere in there. Who knows? But we need to become more scientific than that. So eyeballing it, this is a way that we can do it pretty easily. I kind of know ballpark figure-wise what range we should be working in as far as the base pair fragment goes. But there's a more scientific way to do this. Now, it's not going to seem that way in the beginning. And the reason is because you're going to take a ruler and you're going to measure the distance from the well where it started all the way down to where that fragment appeared. And most of the time, we're going to report these in centimeters. Sometimes we can report them in millimeters, but centimeters is going to be okay when we do it by hand. And then I'm going to do that for each one of the bands. So then I'm going to measure the well, and then I'm going to go all the way down to the 3,500 mark. How many centimeters did it move? Then do it again for the 2,000 mark. How many centimeters did that one move? And then you're going to generate a table. 2 columns. I think you probably know what we're going to do with the data at this point. One represents X, one represents Y. The X will be the centimeters, and the Y will be the base pairs. So as I'm measuring the distances that these fragments move down, and again, I know it's with a ruler, not truly scientific. We can get better than that. But I can at least report centimeter values. So let's say 1 centimeter, 2 centimeter, 3 centimeter, 4. Again, I'm just rounding it off. Then that length is corresponding to a base pair size. And let's say that 1 centimeter corresponded to the 4,000 mark. Let's say the 2 centimeter corresponded to the 2,000 mark. The 3 centimeter, let's say, did the 1,600, and the 4 centimeter, let's say, did the 900. Again, I'm just making them up. I know I skipped 3,500, but I only had listed 4. Now, why is this inverse relationship present? Well, look at it. The smaller fragment sizes are able to move through the gel a little bit easier and better. So they travel the furthest. So smaller, and we've already mentioned this, smaller fragments travel faster, which means that they have longer lengths that they have traveled down the gel. This is an X and this is a Y. The problem, though, with the Y-axis is that very often this will span a very large range. And if you try to plot this just like it is, you're going to get a very weird graph that will begin to appear. And we need to clean that up a little bit. We need to make a straight line because we're going to be after what we would call a calibration curve here. So the way that I clean this up is that I'm going to log the values. So I'm going to log 4,000, log the 2,000, log the 1,600, log the 900. You can do that easily in Excel, and you can also do it easily in your calculator. You just push the log button before the number, and you hit enter. That's all you've got to do. So we're going to take this information and we're going to make a calibration curve. The problem here is that the calibration curve is actually going to trend down. And the reason, again, is because the smaller base pair sizes travel the furthest down the plate. So they have the longer lengths. Normally the calibration curve will go from the origin, 0, 0, up right-handed. This time, though, it flips, and that's due to the base pair size. So on the x-axis, you're going to plot the centimeters, and on the y-axis, you're going to plot the log of the base pairs. And then you're going to use Excel, just like before, to get a y equals mx plus b. And an r-squared value should be close to 1. It won't be 1 perfectly, but it should be close, just like all the other calibration curves that you've made. Now what we can do is that I can take a ruler and I can start from this well and I can measure down to that fragment. And I can report this in centimeters. And this is from my sample, not the ladder. This curve is only made with the ladder information. Samples are treated as samples, just like all the other calibration curves that you've made in the course and the program so far. So this centimeter value, well, look at your axis here. Centimeters was your x value, right? So therefore, in this equation, I'm going to put my centimeter in for X. And I'm going to solve for Y. Now, this is kind of flipped yet again on the standard way that we saw for a calibration curve, but it's just the way the variables kind of shake out this time around. Distance is on the X, therefore distance gets plugged in for X. When I solve this equation for Y, I'm actually going to get a number here. So the Excel will give me the slope, it will give me the intercept. I just plug in my X on that side, I clean it all up, I hit the equal sign, and we'll do an example. And I'm going to get a value, and that value is going to be a number. But I have to understand that this number is the log of the base pair. This number is not the number of base pairs. So in order to get the number of base pairs, well, what we did was that we logged that value, right? So we're going to have to inverse log. And if you've got a scientific calculator, a TI-83 or a TI-84, you're going to very quickly see the inverse log function on your calculator. It's right up above the log button. And that is going to be 10 to the whatever number that shows up there. When you solve for that, that is the number of base pairs that that person has in the fragment, in the fingerprint that begins to get formed in the electrophoresis. So that's how we process, a little bit more scientifically at least, the banding patterns that someone might show in an electrophoresis gel. Now, we've got equipment that does a lot of this for us now. We basically take the gel and we put it onto a gel reader. That gel reader will go through and it will pick out the bands that it sees. It measures the distances on its own, and then it will report those distances to me. It will make its own calibration curve. It will actually solve for the base pairs with using the software. I don't have to do anything to it at all. And this is technology at its greatest. So it makes my job much, much easier, and it makes our numbers a little bit more reliable as well when we get something a little bit more automated, a little bit more sophisticated to do the job for us. So what you're seeing on your screen right now is a picture of one of those pieces of instrumentation or equipment that you might see in one of these working laboratories that do it all the time. So here is the gel imaging system, and you can kind of see the door that's in front. So this door will open up and it will allow you to put your gel or your agarose gel really on the inside of this closed box. A lot of times these gels have to be stained with some type of dye that this plate reader will understand and can see very easily, and most of the time that's ethidium bromide. Ethidium bromide, though, is going to be a highly carcinogenic substance, and that you want to stay away from. You want to suit up, you want to put gloves on, you want to put your goggles on, you want to make sure that you handle it with care because it is strongly tied to a mutagen and carcinogenic. So this is the gel imaging system. We would close the door, and then we would tell the machine that we have loaded an image in, and then it would take a picture of that gel that it sees and that it can interpret. And that picture is you're seeing that over here on the computer screen. So it looks like they have ran multiple different DNA wells on this gel, and that's okay. These gels can come in different sizes, not just the 7 centimeter by 7 centimeter, but they can get fairly large if they need to. I mean, not a problem there. And in each one of those, you are seeing a banding pattern. So could you imagine taking a ruler and going through and manually doing these all the way through? So now we have these imaging systems that can actually take a picture. That way we have a permanent record of it that we can save and transport and transfer and do whatever we want to do with it. And then it will also go through, and some of the software systems will allow you to measure the distances of those bands and report basically the distance of the ladder, and again make the calibration curve for you, and then report the distances that it's seeing on the sample wells, and then applying those to that calibration curve and solving for the number of base pairs. So there's a couple of different companies that do this type of thing. Of course, that technology is out there. It's shared between the major biotechnology companies, biology, genetic companies that are kind of known in the market, and this is just one of them. So we don't have anything as fancy like this as of now. Maybe depending on the year that you're taking this course, we might see one in our laboratory, but as of right now, we do not. Do we have plans on getting one? Not necessarily, not unless we run across quite a bit of money in order to purchase one of these, because of course they are not cheap at all. All right. So that's the story with what we do with the ladder, and that's why the ladder is so important. Again, it helps us to determine the fragmentation pattern and how big those fragments are compared to the DNA standard that we are running, that we are calling the ladder. So we would go through, we would make a calibration curve just like this, and we would process our samples. If we have 5 DNA samples that we were running, we would process each one of them separately, and we would report the fragment sizes on each one for each person. Now, let me kind of do an example for you. That way you can see this process getting done on Excel. So here you're going to see an image, and on the left-hand side of the screen is a gel, agarose gel, that has a DNA ladder on the very first well in what we would call lane 1 or lane A. And then the other samples are just random samples that we have ran from a DNA source. It could be a person, it could be a collection of different things that we're running, but they're just representations of different samples that we have analyzed. And then over on the right-hand side, you're going to see a DNA standard marker. And then this is going to show you a picture of what the marker is supposed to look like. So this is coming inside of the ladder, and you take out this piece of paper and it tells you these are the bands that should appear when you run this gel electrophoresis in the proper settings and in the proper way. And if you look over here to the left-hand side of the screen, you're kind of seeing that, right? You're seeing them add on these bands, and those bands look very similar to the ones that is in the insert. And it kind of tells you the base pair fragments, and they do them in order. So 6751, 3652, 2827, 1568, 1118, 825, and 630. Well, there's 1, 2, 3, 4, 5, 6, 7 different ones. And if you count the bands, there's 1, 2, 3, 4, 5, 6, 7 different ones. They've also listed them in order, and we now know the larger bands will stay on top. So this basically is the 6751, and this bottom one is going to be our 630. So in a laboratory, and they all fall in order in between those. So in the laboratory, I would take a ruler and I would measure the distance from the start, which is this well right up here at the top, and I would measure the distance down to that band, and I would report that probably in centimeter. And then I will do that for each one of these. So that's what an actual DNA ladder looks like, and that's the kind of information that I would get from the DNA ladder insert. Now let me go to Excel. So in Excel, I am going to, let me shrink this down a little bit for you. There we go. So in Excel, I'm going to come over into one of the columns. It doesn't really matter which one. And I'm just going to start typing in the base pair sizes. So we know it was 6751 and then 3652, 2827, 1568, 1118, 825, and 630. So these are the base pairs, and I'm going to label those up here at the top as BP, so that way you'll know what they are. And then I had to go in with a ruler and measure the distance for each one of these. And we're going to report this in centimeters. So in the x-axis, or on the column to the left, I'm going to type in the centimeters that each one of them moved. Again, my biggest fragment will move the slowest, so it will have the shortest distance. And then let's say that I go through and I measure some of the others. So 1.9, 2.1, 2.7, 2.9, 3.2, and 3.4. All right, so now what do I do? Okay, well, let's say that I didn't do anything, right? Let's say that I treated this just as a normal standard curve, and I highlight the two columns for the set of data. I go up to Insert, I go into Chart, I go to Scatter, and now I see this non-linear curve, right? And I warned you about this. And the reason is because some of these are really large numbers, some of these are really tiny numbers, and they don't really move in a linear fashion. So that is not the type of curve that we want. We want something that has a straight line with it. So I'm going to erase this, get rid of that chart, and this is where we're going to have to go in and do the log of the base pairs. So the way that you can get Excel to do this, it's fairly easy. I'm just going to, up here at the top, just put the log of BP on it. You're going to start off with equal because this is a calculation, and Excel will understand that it needs to calculate something. And I'm going to type in log, and then I'm going to open the parentheses up, and then I'm going to click the 6751. And it types in C2 reference for me. Then I'm going to hit enter. So there is the log of the base pair. So I'm going to click that box. I don't want to do this over and over and over. And there's a small little square in the bottom right-hand corner. I'm going to click it and I'm going to drag it down. And that will automatically calculate the log of everything for me. So this is the log of 1.9, the log of 2.1, the log of 2.7. And I can see those numbers are changing as we go down. So now I'm going to highlight the X variable, or the first column. This has my length. And then I'm going to hold down the control button, and then I'm going to highlight the second column that I want it to plot. That way, if I click and drag, it's going to include this third column, and I don't want it to include that third column. So highlight, drag, hit the control, and then drag your second column that you want it to plot. Then I'm going to go to Insert, just like before. Then I'm going to go to the dots for the scatter plot, and then I'm going to choose just the dots only, right? And now we can see a better fit straight line. Now, how close or how good are we? Well, let's figure that out. So I'm going to click on one of the dots. It doesn't really matter which one. And then you're going to right click once it highlights the set, and you'll go down to add the trend line right here. So right click on a point, hit add trend line. This prompt box will show up on the right hand side. Scroll to the bottom, click display the equation, and display the R squared value. And then I'm going to X out of that box, and there is my line. So negative, I knew it was going to be negative. It tends to go downward. 0.5404 plus 4.6317, and my R squared is 0.9895. All right. We would really like to have a 0.995 or higher, right? I mean, that's kind of what we're after with all of our points, but this is not too shabby. I mean, I'm measuring it with a ruler. There's probably some error that's associated with that. So this is kind of expected. No big deal, right? I'm not worried with that, but that's pretty good. If you look at all the points, I mean, that line typically goes through all of those points, right? So now let's say that we have a fragment with a sample. And let's say that that length is, we have measured it, and it is a 1.7. So I need to figure out how on earth do we go about calculating this base pair fragment size based on 1.7. All right, so I'm going to bring my calculator over into the screen. And 1.7 is plotted on the x-axis. That's the length, right? So that means that it needs to go into the x variable here, 1.7. So in the beginning, this is going to be pretty easy. I'm going to take 0.5404, and I got to make sure that's the negative. Then I'm going to multiply that by 1.7. All right. And then I'm going to add 4.6317. So just plug it into X, solve the equation, and this is Y. Y is 3.71. Right now, that's the log of the base pair, 3.71. So if I just kind of eyeball it, it looks like it should be between 6751 and 3652. That's where this number is going to lie. So if I do this calculation the right way, then there's kind of the estimate window that I need to be looking for, right? And 1.7 would have also told me that. 1.7 is right in between 1.6 to 1.9. So I know it's going to be between 6700 and 3600. So this is the log of the base pair, not the actual base pair. And we talked about how to do this on a calculator. So in order to do the inverse log, it is 10 to the, and this is going to be 3.71302. All right. So on this calculator, here's a 10 to the x. So I'm going to click it. And it looks like it's already done the calculation for me. It's as easy as that on your calculator. You would have done 10 to the, and you would have typed in 3.71302. And now this answers 5,164. So 5,164. That is the size of the base pairs, or the fragment, that showed up at 1.7 if it did that on the DNA gel. So again, I would go through each sample and I would measure the distance from here down to that one, and then from there down to this one. And this I would report both for that sample. This DNA sample only has one, therefore I would just report one fragment size. This DNA sample has two, so therefore I would report both sample fragments that I have seen in that lane. And then finally, this one over here looks like here's one, and it looks like one showing up down here. Very faint, but it looks like it's there. So again, I would report on both fragments and how big each one of them are. Okay? So that's how we process the ladder. That's how we make a calibration curve. That's how we determine the number of base pair fragments that we have in each one of the bands that show up on your DNA ladder. All right, so that's where I'm going to stop this video. I think that was enough. And then in the next one, we'll continue on with this analysis of DNA, and we'll talk more and more about what's required in order to do this in a laboratory environment.